All right, let's go ahead and get started. So we've got a exam on Tuesday. So what we'll do this morning is first hour or so, we'll go through some practice problems, look at some things that you might see on the exam, and then we'll continue with elimination reactions. So whenever we stop, I'll draw a line like I did last time, and anything before that line will be on the exam, and anything after will be on the next exam. Online homework is due on Monday night. We'll have office hours today at 10 o'clock, and then I'll put some on for Monday afternoon and send you an email on that one. So same process as last time. If you can't be here because of isolation or quarantine, send me an email. By Monday, I'll send you the email so you can just send it back. And just let me know you need it by distance. Again, because of the stress and stuff of taking it away, if you can be in campus, if you're feeling well, come take it in class. It's easier. The only difference is driving, but it is less stressful than having to worry about scanning the test and getting it back. Okay, so let's look at some practice problems here. So this is kind of exam 2 practice, and this will not be in order of how it'll just be as I have some examples from some old exams here. So the first question is, which of the following, and I'll change colors in a second, is likely to rearrange by a 1,2-methyl shift? So if we looked at these 4 groups here, let's take a little while, take a look at it, look at the carbocation, what's next to the carbocation, and tell me which one of these 4 would likely do a 1,2-methyl shift. And I'm going to set a little timer because whenever I'm sitting here waiting for y'all to finish these, time goes really fast, and for y'all it goes really slow, so that we're on the same perception of time. I'm going to put a timer. So. I can turn it off. It's in my ears. Okay, so if we look at this one, the first thing I would do is start looking at the different carbocations. Okay, this is a secondary carbocation. This is a secondary carbocation, primary carbocation, secondary carbocation. And the next thing to do is look at what's next to it. Here I have a secondary position. Okay, would there be any advantage of getting some type of shift here? No, there's also no methyl groups, but I don't see any advantage, right? If I shifted that, I'm not going to get it. And you also usually do not see multiple shifts unless there's possible resonance. Here, again, I've got a secondary position, but now I've got a quaternary position next to it. Okay, this would suggest that I potentially have a shift, right? I've got a difference of 2. If I shifted one of those carbons, those methyl groups, I should see a change. Here, I've got 1 and then 4, right? Again, this is a possibility. And then here, I've got a secondary and a secondary. So right now, that would probably be enough to answer the problem. I'm going to go ahead and show you what the product looks like so you can kind of see. This is also a step that you can add in there just to check your answer. Okay, so if I move that methyl out to this position, that would leave the carbocation here. If I evaluate that carbocation, I see that that's a tertiary. So going from a secondary to a tertiary is going to be energetically favorable. That's going to predict a 1,2 methyl shift. In this one, I've got the methyl out here on the outside. So again, if we move that methyl group over, leaving me the positive right there. I've gone to a tertiary. So I've gone from a primary to a tertiary. So again, that would be favored. So the 2 that I would expect would be these middle 2 in the middle. Yes, sir. I'm not quite understanding. You wouldn't potentially have all these carbocations as the same. So they're not actually in competition of each other. The molecule that would result in this carbocation is not the same as the molecule that resulted in that carbocation. So you're not comparing them, you're just looking at those 4 base structures independently and saying, could they rearrange or would they rearrange? This one's not going to rearrange, that one's not going to rearrange, right? These 2 could, and these both would get a more favorable position. I'm not comparing these 2 or those 2 together. Again, they're not in resonance, so they're not 2 different pictures of the same molecule. Now, if we thought about forming these, so if we started with the alkyl halide here and the alkyl halide here, right, this is going to be a faster reaction because I start with a secondary alkyl halide going to carbocation. This is a primary, right? This would be a very tough reaction to get. That wasn't what it was asking. It's just like, if I had these, which ones would rearrange? Okay. And again, kind of getting to that layering idea that we ask questions based on one concept. And the concept here is, can you recognize what would rearrange? Okay. All right, questions about rearrangements? Yes. Yeah, if it's still 1, so we see here we go from secondary to tertiary, right? So it's still stable enough, right? A 1 to 3, right? That's a big jump. Usually what you see is 2s to 3s, right? Every once in a while, 3s to 4s don't really work. So 2s to 3s is what you get. So. Okay. Let's look at, so this one is a which mechanism? Again, let's take about 30 seconds, look at this one, evaluate it. When you see one of these, I haven't put the choices down here on a multiple choice test. You'd have the choices. But one of the first things to just say is what is happening in the reaction, right? What's occurring going from this side to that side? Is this a substitution? Is this an elimination? Or is this an acid base? Well, it's a substituting, right? I'm substituting that chloride for this alkyne group, right? So the first thing we know is that this is a substitution. So not on this test, but the next test, you'll be asked whether it's substitution, elimination, addition, right? You'll have several different choices, and then you can eliminate a lot of the answers by just knowing what's occurring. This case is a substitution. It's not elimination, not an addition. It's just a substitution. Okay, but there are two substitutions, so therefore I need to start putting the rest of the data in there. What does the substrate tell me? And again, we can kind of go through them. Substrate, primary. Primary would suggest SN2, right? Non-hindered electrophile. Okay. What about my nucleophile? That is a good anionic nucleophile, right? And what do we know about the steric hindrance of it? It's non-hindered, right? Because it's more or less just a nucleophilic arrow. It's all in the same plane, right? This is SP, right? So that means that's linear. We can think about it as a nucleophilic arrow. Then our leaving group, chloride is a good leaving group, right? We don't have to activate it. Halides are good leaving groups. You'll see them lots. And then we can look at our conditions, right? Solvents are usually underneath the arrow. So this DMF is dimethylformamide. It's one of the aprotic polar solvents you'll see. Okay, your class of aprotic solvents that you'll see most often is acetone, DMSO, and DMF. Okay, so it falls into that group. I'll show you in a second, if you didn't recognize that solvent, you could still get the answer here. But since that's a polar aprotic, this would suggest what? SN2. Okay. So if we look at what's going on here, we have SN2. You know, this suggests SN2. The leaving group is a good leaving group. I don't have to worry about protonating it or anything before. So it could be SN1 or SN2. So those two right there tell me this is SN2. If I knew DMF, I could confirm that again with SN2, right? So I've got three things that are SN2, and I have a good leaving group, which could be SN1 or SN2, right? So that means that my mechanism here is going to be SN2, right? So evaluate each of those parts. If you don't recognize a solvent, that shouldn't determine the answer, right? You should be able to get to the answer without recognizing a solvent. If you do recognize a solvent, it can help. And again, aprotic solvents favor SN2, protic solvents favor SN1. Okay, questions about this one? Okay, so product. So what's the product of this reaction? while you're doing practice, it's always a good idea to make sure you know what's going on with your reagents. So we tend to use abbreviations quite a bit just to make it easier to do things. It's a lot easier to write TCL, TSCL, and PY than it is to write both of these. But as you're practicing, it's good to do that, right? Now, what is the reaction that's occurring here? Is this going to be an acid-base reaction, a normal proton acid and base reaction? Is this going to be a substitution, a normal carbon electrophilic substitution? Or is this an activation of a alcohol to become a leaving group? Well, it's an activation, right? So what I'm doing is I'm converting my alcohol to the tosylate. Now, the things to notice here is what is doing the attack. We'll go back over here and put our electrons. Are we going from oxygen to sulfur? Or are we going from sulfur to oxygen? Okay. Well, we're going from oxygen to sulfur, right? The lone pairs on the oxygen are attacking that sulfur, and we get this kind of hexavalent intermediate. Therefore, did the bond between the carbon and the oxygen ever change? It was never touched, right? So therefore, did we ever have any reason to change the stereochemistry? No. Okay. And this is one of those where it's actually easier if you cover up the answers and you just answer it, because here were all of the answer choices on this old exam. Now, if you knew what a tosylate did, that gets you to 2 possible answers, right? But at this point, then you might get confused and pick the wrong one, right? You might have forgot that. So just going through and answering it and covering up the answers can help you on these, because the distractors are there to distract you. So cover up the distractors, answer the problem, then choose the right answer and put that down. Questions about this one? Yes. This one is, it is a substitution, but it's a substitution on the sulfur, right? It's not a substitution on the substrate. So this is the subset that we use in organic is activation of a leaving group. Okay, but the effective, if you're looking at substitution, elimination, addition, it's a substitution on the sulfur, not the substrate. So therefore, looking at it from the substrate standpoint, you activated the leaving group. Okay. All right, other questions? Yes, ma'am. Yeah, I ended up with the Cl attached to the pyridine. Yeah, so if you look at the whole mechanism, so I'm just going to start from what I drew up there. Oops, and let's do a different color. Yeah, so you don't change this stereocenter, but then you have this group. Then the oxygen negative comes down, kicks off the chlorine. Oops. And we've got to remember we still have a proton here. Kicks off the chlorine because the chlorine's pK, conjugate acid pKa is actually lower. Again, we haven't changed our stereocenter. Now we have our fully tosylate formed. We have the chlorine floating out here. We have the positive. And then the last step is that pyridine. coming in and pulling off that proton. So the, I guess the bystander process is forming that pyridinium chloride. So the chloride just goes to wherever the positive is. The pyridine pulls off the hydrogen to finalize the product. That help? Usually when you're dealing with like the bystanders, the non-substrate in organic, we usually don't show those reactions unless we're talking about the mechanism. Okay, so here it's not necessary for you to show it's not necessary to show that as the byproduct. Okay, it's not reacting to the substrate. In reaction, we'd actually wash this out or recycle it. You'll see the same thing whenever we have like a substitution of, like, say, a sodium methoxide with a bromide. The byproduct is sodium bromide. We don't often show the sodium bromide, right? The methoxide substitutes for the bromide. The resulting byproduct is going to be sodium bromide. So here, the pyridinium chloride is the byproduct. So it's not necessary to show it as a product. We always show all of the byproducts when we're doing mechanisms. This group here? This one here? Oh, but this is a second step. Only the first step. Right, so I only showed you this part of the reaction. So if we go back, right, there's only one set of reagents. So it's only the first step. There's only one set. And remember, this is not, those weren't those weren't one coherent reaction. It was activation followed by, right? So therefore, the second step could be any nucleophile. So all I'm showing you here is the first step, the activation of that group. Now, if I had a 1 and a 2 here, right, had another, then you would have done the second, the substitution. So this is activation, you would have followed it by substitution in most cases. But right here, I'm just asking you, do you know what the activation product is? And again, that's where the distractors become difficult. You know, if you remember the way the reaction was done in your notes or on a previous homework problem, you may go too far and go ahead and assume the chloride is being substituted, right? But what we're here is just the first step, just the activation. Okay, yeah, good question. Okay. All right, let's try another one. So let's take a little time on this one. In this case, they're telling us what the mechanism is. It's going to be E2 mechanism, right? We could have figured that out from a bulky base and the low temperature, right? Low temperature would suggest that we're going through a concerted mechanism and not a carbocation. High temperature would suggest a carbocation. But here we're looking at the beta hydrogens. So we have the blue beta hydrogen and the purple beta hydrogen. Since it's E2, what do we need to know besides just beta hydrogens? Not only does it need to be a beta hydrogen, the beta hydrogen must be able to do what? Must be able to form an anti-paraplanar arrangement. So that means we need our leaving group and our hydrogen, right, on opposite sides, because we're going to want the electrons. The base is going to pull that proton and the electrons are going to have to come in from the backside. So of these two hydrogens, which one can form an anti-paraplanar to that bromide? Okay. The one that's on the backside can be anti, right? If we get the right chair conformation, that can get anti. The best we can do with this hydrogen is gauche, right? So this one can't form an anti-paraplanar, this one can. So therefore, the only product from this will be elimination of this hydrogen to give us this product. In this case, I did 2 methyls. That's clear enough, but usually you'll see I'll use propyls or ethyl groups just so that they're more easily distinguishable. Yes, ma'am. Now it's in the plane because it's gone from an sp3 to an sp2. Right. So when I went from the sp3 carbon that has 3-dimensional shape, I've now gone to an sp2 carbon that's planar. So this change is due to the hybridization change creating that double bond. All right, questions about that one? If this had been an E1 mechanism, then I would have gotten 2 products, right? Because I wouldn't have had the same anti-paraplanar arrangement. There's no stereo control in an E1, just like there's no stereo control in an SN1. Let's do another predict the product. let's take a look. So if we look at this product, the first thing we might need to do is think about what's going on here. The NH4 is actually a positive, so we can think about that. Okay. The NH4 is positive, so you might want to think about that as your sodium, potassium, and ammonium iodine. I'm sorry, sodium, potassium, and lithium. So that's positive, so whatever's next to it is negative. So we're dealing with a cyanide anion here. If we look at our substrate, we have a secondary substrate. Okay, secondary substrate could be SN2, but you know, it's also probably SN1. So SN2 non-stabilized is probably going to be favored, but SN1 is not excluded. Okay, so this is one of those where there's a preference for SN2, but SN1 is also fully possible. When we look at our nucleophile, we have a good nucleophile, actually a great nucleophile. Right, it's anionic and it's non-hindered. Right, both of those suggest it's going to favor an SN2. We have a great leaving group. Right, iodine is better than chlorine or bromine. So again, this could be either SN1 or SN2, but because it's big and polarizable, there's a slight preference for SN2. So we have one SN2, we have two possibles, but both with preferences to SN2. And then if we look at our solvent, and again here, because I could probably say SN2 at this point, but the solvent here is going to clinch it. Again, solvent by itself won't clinch it. But with everything else there, if I get another SN2, this is an SN2 reaction, right? And so with this is DMSO. You don't need to remember the structure, but the structure helps you see what's going on. This is an aprotic solvent. And it's polar, right? So it's polar aprotic solvent. So that's going to favor SN2. Right? So with all of this evidence, this is an SN2 process. And since this has got a stereo center, I'm going to be looking for inversion. So it's always good to draw the mechanism. The more you get the mechanisms in your head, the more you'll understand how things are happening versus just guessing how they're happening. So we get backside attack. Kick off it's kind of ugly. Let me redraw that. And we get an inversion of that stereo center. And the way we can show that is just by moving the hydrogen forward. So we can think about it as kind of an umbrella flipping, right? You've got an umbrella, it's Oklahoma, you've got a strong wind, and the umbrella flips the other way. Okay, questions about this one? And again, the same thing could have occurred if we saw SN1, 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 SN1. In that case, we would add an inversion and retention, and we would have gone with that answer. Oops. On this one, it is give the products and conditions. Sorry, reactants and the conditions. I'll fix that in just a second. Okay. So let's take a little time, think about this one. What is going to be the nucleophile you substitute? What kind of conditions would I want to get this product in high yield? Okay, so if we look at what's being substituted, this part of the substrate, right, is staying the same. So really what we're doing is we're substituting that bromide. So if we look at what's being substituted, we're substituting that. So that needs to be part of the reactants. That has to come from somewhere. So it's got to come from reactants. If we think about it, we have a couple of possibilities, right? We could have the protonated form or the anionic form. In this case, which one do you think would be favored? Well, that comes back to our substrate and what is the electrophilic position. That's the electrophilic position, right? And it is primary. So if it's primary, is this going to be favoring an SN1 or an SN2 right off the bat? SN2, right? So therefore, this would be the better one. Of course, that's not a reactant. That's what actually is reacting. How do I turn that into a reactant? Well, I say sodium, right? Or I could say potassium, right? So it could be sodium propoxide, or it could be potassium propoxide. It could be ammonium propoxide, lithium propoxide, right? I just need to have a cation there. So I've got several possibilities there. Multiple choice test, pick the one that makes sense, right? That it's a propoxide. In a free response test, I understand that these are just counter ions, so I'll count them all right. Okay, now that's that part of it. Is there anything else here as far as conditions? So if we're wanting to go this SN2, right? So this looks like an SN2 reaction, then what other conditions do we want? Do we need a lot of heat? No, this could probably be done at room temperature, right? What about solvent? Do we want a protic solvent or a aprotic solvent? Okay, so for our conditions, right? Room temperature is good, right? Lower temperatures. No reason to heat this up. Right? And our solvent, we want an aprotic polar. So if I gave you choices of water, ethanol, hexane, or DMSO, which one would be a aprotic polar solvent? Well, water's protic, right? It has a hydrogen bonding hydrogen. Ethanol is protic.